Good afternoon as well to everyone.
Welcome to this plenary session of today. It is a great honor to have you here, and we have two fabulous speakers for the coming hour. So let me not take too much of your time, but encourage you to post questions in the on-air Q&A directly if you have any. During the talks, so that we can monitor that. I know that the youngsters among you tend to prefer Slack, but let's try to put it in on air. If you can, it's a bit easier to do that, but we will all be swapping between channels anyway. So without further ado, let me introduce the first speaker, Professor Ignas Snellen from Leiden University. He has been gradually building up a major recognized team in all sorts of research topics, but above all exoplanet research. And today he's going to give you a talk on exoplanetary research and particularly on the search for extraterrestrial life. Ignas, please.
Thank you, Conny. Let me put up my slides. I hope you can all hear me well. Thank you very much. Very nice that you're all listening in. A real pity that you are not in Leiden, because yeah, it would have been very nice to drink a beer, but maybe we'll have to do this another time. So I'm going to talk about exoplanets and the search for life. Wait 1 second. I'm not sure whether I'm sharing my screen and my laptop freezes.
We can see you now, but we cannot see the screen.
Wait 1 second, I did something wrong. Yeah.
Here we go.
Yeah, that's much better. So can you see me now? And can you see me?
We see you in the portal app.
Actually, Ignas, if you share your screen, you should share the PowerPoint slide. Yeah, not the screen view. Stop sharing.
Yeah.
Here we go.
Now you can see me and you see the slides.
Yes.
Yeah, okay, thank you. Sorry about that. So I'm going to talk about exoplanets and the search for life. Well, if you've been working for a long time in the field, then you sometimes forget that only 25 or 30 years ago, the only planets that we knew were the planets in our own solar system. And then, of course, there was the big change with the actual discovery of 51 Pec, now rewarded with the Nobel Prize, something the field we can all be actually proud of. And that really set an onset of a real revolution. Now, several other planets were found very quickly. The first planet transit a few years later, measurements of atmospheres, the first measurements of planet thermal emission, and then also moving away from hot Jupiters towards other planets like exo-Neptunes. And the first thermal maps were found, the first photographs, the first direct imaging, measurements of molecules, evidence for winds, and really the number of planets just is moving further and further up to 1,000 exoplanets already in 2013. And then a big breakthrough in 2016 when the first exo-Earths were found, like Proxima b and the TRAPPIST-1 systems. Yeah, these are planets with the mass and radius of the Earth, but also which could have a very similar climate. So actually liquid water could actually exist on their surfaces. Now this revolution is not here because we are getting smarter and smarter, maybe you know, a little bit, but mainly because our instruments are getting much better. You know, if you only think about the radial velocity measurements, now the accuracy of those since the 1980s has actually increased by about a factor of 1,000 or so. So this means, because we know what instruments are coming online, we know the great observatories, James Webb and the ELTs are coming there, so we can already peer a little bit into the future and see what we can do. You know, we can move away from the very warm, big gas giant planets towards atmospheres of Neptune and even mini Neptunes and super Earths. And what is really exciting, we could even start to probe the atmospheres of Earth-like planets like Proxima b and the TRAPPIST-1 system, and maybe even find out whether they have biomarkers or not. So this is really what my talk is going to be about. I'm going to show you what we can do now and how we actually got here, and how we think this path is going to be like in the future. So maybe it's first to actually talk a little bit about why are we actually doing this. So if I give an actual public talk, then I often get a bit of a negative questions like, why is this actually interesting? Finding another Earth hundreds of light years away, we can never actually go there. Well, it's not really about finding these other planets themselves, but it is about learning about ourselves, about humanity and the place of the Earth and the solar system in the universe. And there are many questions we can ask ourselves. How do planets form? What kind of ranges of architectures of planetary systems exist? And how does the solar system fit in? Is the solar system in any way different? And if so, why is this actually the case? And then, of course, there is the 100 billion euro question about whether other life-bearing planets exist, or whether we are actually alone here on Earth. Well, and I think this can be really, from a philosophical aspect, this can be really important, because I really see this, that we can influence the way humanity looks at itself and at the Earth. In the same way that Galileo did a long time ago, and that Darwin did, and maybe more recently, the first photographs, the actual Apollo mission brought us, seeing Earth as an actual whole. I think finding the first evidence for extraterrestrial life can do a similar thing. So, of course, there are planets that we know very well. These are the planets in our own solar system. And so if we look at these planets, if we look at those planets sort of in a very broad way, what can we learn? Well, one thing is, of course, very obvious, and that is that the complexity and diversity of these planets is just enormous. Now we see here the four rocky bodies that have an actual atmosphere: Venus, Earth, Mars, and Titan. Well, Venus has a super rotating CO2-based atmosphere with opaque sulfuric acid clouds. The Earth is very different, has a nitrogen-based atmosphere, partially clear, large fraction of oxygen. Then Mars has a very thin atmosphere again, and is CO2-based, with, for example, trace amount of methane we don't understand. And then Titan has a nitrogen-based atmosphere, very cold, but also a thick cloud layer. So how are we ever gonna make some kind of a structure out of this mess? Well, I really like to actually compare this with one of my heroes I already mentioned, Charles Darwin. What if Darwin would only know about 3 species? He would have known about an owl, an ape, and an actual scorpion. Now, of course, he would never be able to learn about this great theory, how to understand the tree of life and how this all came actually about. Well, I also think like that about the solar system. Knowing about Mars and the Earth and Venus is not enough to understand the structure of planets and how they form. We really have to go like Darwin, who went on this epic voyage, go around in the exobeagle, around these distant shores and coastlines, to find out about all the life that is actually out there. I see the exoplanet field also a little bit about, like this journey, like this epic journey. It's going to be very difficult, it's going to be hard, but we need to do this to really understand planetary systems as a whole. So where are we now? We now are 25 years on this journey. Well, what have we learned? Well, it's clear planets are everywhere. Thousands of planets have been found, about 4,000 now, I think so. And what we have learned already is that the diversity is even larger than in our solar system. There are all these planet classes that do not actually exist here. For example, the hot Jupiters, of course, the first ones we know. Gas giant planets in very short orbits. We don't really know how they are formed. Then there are these super Jupiter planets, very massive, very wide orbits, hundreds of AU away. We also don't know how they actually get there and how they are formed. And there are this very common class of super Earths and mini Neptunes. That is one of the most common planets in the Milky Way. And we do not see that in the solar system. As I just said, planets are very common. We see that about 1 in 10 have a Jupiter mass planet, 1 in 5 have an actual Neptune, and most stars have Earth mass planets. So these are very common, and we can already see that, you know, because Proxima b, you know, our nearest neighbor, has an Earth mass planet. It's about now 1.1 times the mass of the Earth. It's in a bit more than an actual 11-day orbit. And because the luminosity of Proxima is so low, this means that it actually receives as much starlight as the planet would do around the sun in an orbit somewhere between the Earth and Mars. So it could well have liquid water on its surface. Now, and the same for the very exciting TRAPPIST-1 system. It has 7 sister Earth planets, of which 3 or 4 could have liquid water on their surfaces. So when we start to characterize planets, what kind of questions can we actually ask? What are the things that we want to learn? Now, first of all, of course, we want to understand what the bulk composition of a planet is, and whether the planet has an atmosphere, what kind of molecules are present, what is its climate like, what is the difference between the day side and the night side, how cold and warm is it? Do we understand all these things in the context of its formation and evolution? And then also, do we understand the physical and chemical process, and probably, possibly how it is linked to any geological processes? Now, if we then home in on the Earth-like planets, then we, for example, want to know, is there any water? And if so, at what level? Do we see any biosignature gases like molecular oxygen, ozone, or methane? And then, of course, the most difficult question is, if we would see such a gas, now, are these gases really due to biological activity or not? Well, there's a lot of research in that area going on, and we already know from theory that there are other ways to make oxygen. Of course, on the Earth, it is due to biological activity. But for example, there are other pathways. If there is a rocky planet and it had a deep ocean that actually evaporated and the hydrogen escaped to space, then the oxygen molecules stay actually in the atmosphere and can in that way build up an atmosphere rich of molecular oxygen. But the good thing is that luckily these same models show us that actually we can separate out these different pathways by measuring other molecules, the presence or not of other molecules in the atmosphere, like CO, CO2, or methane. Now, so how can you actually measure molecules or other properties of exoplanet atmospheres? Well, you have to realize that although thousands of planets have been found, most of them have been found without identifying a single photon coming from the planet themselves. If you do atmospheric measurements, you no longer can do that. You really have to separate out the light which is coming from the planet from the light that is coming from the stars. Now, basically two families, ways of doing this. There is the time differential method. Here we talk about transits, eclipses, and phase curves. And this really takes into account that on different times we see the planet light differently. And then there is the sort of angular differential class. This is really the direct imaging, spatially or angularly separating out the planet light that is coming from the actual star. Now, both methods work best on very hot planets. For the time differential methods, these are the hot Jupiters and very short orbits where things change very fastly. And then for the angular differential method, this is for planets which are very far from the host stars, but are very young and therefore still warm from their formation. Both methods have actually achieved already many things, both for hot gaseous planets. These are many molecules have been found, atoms, ions, temperature structures, both in the vertical and longitudinal way, evidence for atmospheric loss, Rayleigh scattering from hazes, evidence for clouds. The mean particle mass can be found from the scale height, evidence for global circulation patterns, and direct measurements actually of global atmospheric winds and planets' spin. So there is one thing we're all looking forward to very much, and that is of course the launch of the James Webb, hopefully very soon. Also the ESA Ariel mission will be very exciting a few years later. These missions will really focus on transit and eclipse spectra. And with the James Webb, this means we can really move away from these hot giants that we are mainly doing now to the cool Neptunes, mini Neptunes, and super Earth. Now, what is really nice, and this is what I really like about this field, things are changing so fast. If you think that this TRAPPIST-1 system was only found 3 or 4 years ago, a few years in the future, we can already start to probe the atmospheres of these planets with MIRI. You see here on the bottom left, there is the brightness temperature, models of the brightness temperature of TRAPPIST-1b as function of wavelength. These are the MIRI wavelengths. And what you expect here, that if the planet has an atmosphere, then the difference in temperature between the day side and the night side will be much smaller than if the planet does not have an actual atmosphere. There's just, you can see the atmosphere as a kind of a temperature regulator for the day side and for the night side. So by measuring the secondary eclipse, for example, at 12 micron, you can actually derive what the day side temperature of this planet is, and in that way find out whether it has an atmosphere or not. But you can even go a little bit further, and that is if you go to 15 micron, if it is a CO2 based atmosphere, you actually would expect that a strong feature from CO2 there, and therefore the secondary eclipse feature should be significantly weaker. So by measuring that, you could even already identify whether there are molecular gases and what molecular gases will be present in the atmosphere. This is really exciting, and this is something we can do very soon already. There is the actual MIRI team will actually do this already very early on in the mission with guaranteed observing time. Now we can already do something along these lines now. There is on the right, on the bottom right here, a recent measurement of Laura Kreitberg, who by the way moved to Europe last week. She is now the new director of the MPI Institute in Heidelberg. So I'm not sure whether she is actually online now, but a warm welcome to Europe. I'm very happy that she is going to join us here. She did a great observation of a very hot planet. It's much hotter than the actual TRAPPIST-1 planet. It's only in an actual 11-day orbit. 11-hour orbit. So it's very short. It's 1,000 Kelvin planet or so. And what you see there is that this is a phase curve, that the day side temperature is very high, but the night side is extremely cool. And this means that actually you cannot understand these observations if the planet has an actual atmosphere. So for this very hot planet, it is clear that in some process, the atmosphere has been lost through the lifetime of this planet. And that is not so strange. That is what you would expect for such an object. But what I just said is that the TRAPPIST planets are much cooler, and therefore there you would expect an actual atmosphere. And because the MIRI will be orders of magnitude better than the actual Spitzer is, we can actually do this soon. Now, if we talk about ground-based observation, what we have learned over the last decade is what works very well is to combine these two types of classes of observations with high dispersion spectral methods. So what you do here, so you don't only use the time differential and angular differential way to separate out planet light and starlight, but also use the spectrum. And that's because you expect the spectrum of the planet to be different from that of the star. That could be because, for example, the planet has molecules because it's much cooler, but that could also be because if you, for example, look for reflected light, is that there is an actual Doppler shift between the planet and that of the star. And you can use these elements to further probe deeper into the glare of the starlight. So we started with this in my group about a decade ago. And what we do is really use high dispersion spectroscopy for this, typically at a resolution of 100,000. And what happens here is that when you probe an actual band, is that you resolve the band into tens or sometimes even hundreds of individual lines. And due to the strong Doppler effect, due to the orbital motion of the planet, now for the Earth this is 30 kilometers per second, but for a hot Jupiter this could be up to 100 or 150 kilometers per second. Already in 1 or 2 hours of observation, actually the Doppler shift makes the planet lines drift through the spectrum. And this helps you to separate out light which is coming from the planet from the stationary lines that you expect from the Earth's atmosphere and from the star. Now here on the bottom you see a few examples of some early work that we did, mainly on carbon monoxide on a hot Jupiter, both in transit and actual day-side measurements. But because of time, I want to move very quickly to some recent work by some other groups. For example, here on the left, there is very nice work by the University of Amsterdam using the HARPS North on the TNG, where you have to concentrate here on orange on the top left panel, where you see if you squeeze your eyes a bit, you see here in the velocity on the x-axis and planetary phase on the vertical axis, you see actually a trail of iron in the actual data. In the middle panel, you can see a model so that can guide your eye a little bit. This is an extremely hot planet. It's Kelt 9b. It's in a very short orbit. It has a day-side temperature of 4,000 Kelvin. And this is so hot that actually this atmosphere is glowing in iron. And that is what you see in this very nice observation. Now on the right side, you see a very recent measurement with espresso published in Nature by the Geneva group. And what you should concentrate on here is yellow, because yellow is, again, this is observations of iron, but now not from the day side, but during the transit of another very hot Jupiter, was 76b. Horizontal axis is now, again, velocity, but now in the rest frame of the planet. And the vertical axis is time. So in the bottom, you see the beginning of the transit. And the iron absorption is a little bit blue shifted, but this blue shift increased enormously to about at the end of the transit is about at 15 kilometers per second. So this is 50,000 kilometers per hour. This is just amazing. So what's happening here is they have a very nice model for this, what's happening. So during the actual transit, the planet is wobbling a little bit. In the beginning, you see more of the morning side, while at the end of the transit, you see more of the evening side. And what they see that at the part of the transit where you only probe the part of the atmosphere which is just before the sunrise, that there is actually no iron there. And what that means is that at the night side, there apparently the iron rains actually out, because at the evening side, the iron signature is very strong. So I think this is quite amazing that, you know, this is a world a few hundred light years away, and we can actually say something about the weather. Not a planet you want to visit, by the way. Okay, why does this work so well from the ground? This is because this is really a double differential method. We have in one way, we do differential in actual time or in actual angle. And on the other way, we do a differential in spectrum. And in that way, you can calibrate out any signatures from the star and from the Earth's atmosphere very well. And that's the main reason why you can do this so well from the ground. The only downside is that you need an enormous amount of photons. For example, some of the work we did on Tau Bode's, this is, you know, is a 4th magnitude star. We needed 3 nights of observation on the VLT to show the carbon oxide signal. So we want, of course, a bigger telescope. And that's the reason why we are so excited about the ELT. There are 2 instruments which are very interesting for us. There is a first light instrument METIS, which had an integral field unit at the resolution of 100,000 between 3 and 5 micron. And then there will be a 2nd generation instrument HIRES, which will cover the optical and the near infrared. And just to give you a bit of a snippet of the things that we can do, this is really mouth-watering, I think. In green here on the left, yeah, this is for a hot planet. Now, what if we stare for a night or a few nights on a hot Jupiter? What you could do, well, you know, look at the bottom spectrum. This is really a spectrum you would expect from an actual star. You know, you can really start to probe molecular abundance of function of day side, morning, evening side, night side, and look at the detailed temperature structures and see how they actually change. Then in the middle panel, which also I think is very exciting, we can start to look at isotopes. This is something we are trying already now on the VLT, see what we can do. For example, for the hot Jupiters already. But what we show is that actually for METIS, we can start to probe the HDO versus water ratio. And this is very interesting if you want to look, do you want to get new insights into the history of these planets, and for example, what kind of an atmospheric loss they actually have. And we show with simulations that we expect we can actually do this for Proxima b as well. Of course, as long as this planet is actually a water-rich world.
Ignas, I think Conny wanted to give you a time warning, but doesn't get through.
Ah, okay.
So it's 3 minutes left in the session.
This is perfect. And on the right side, on the bottom here, we see maybe the ultimate science case. You know, could we actually observe molecular oxygen? Now, this will be in actual transit measurement. This will be very difficult for the most nearby Earth-like planets that it's orbiting mid or late M dwarf. This will maybe just be possible adding up a few dozen transits or so. But there is another method, and this is the last part of my talk. You can also combine this high dispersion spectroscopy with direct imaging. And this is very exciting. This is an idea that has been around for several decades already, but it has now really starting to blossom. And let me explain this a little bit in the blue picture here to the left. So this is a typical direct image. We see the star in the middle, and there is a small planet to the actual bottom here. But there are also these smudges very close to the star, and these are quasi-static speckles. But you really want to know whether some of these blobs are actually planets or not, but you cannot do that. However, if you have the spectral information, you can start doing this, because the spectrum of the star is different from the planet, and therefore that helps to separate out the planet light from the star, and you can probe much deeper in the actual vicinity of the star. Now, very quickly, on the right side here, I do an example. This is with Symphony at a low spectral, or at the spectral resolution of 4000. This is in white light. All the image cube here completely dominated by starlight. But we know the star spectrum very well, and we can therefore remove it from every pixel. And what is left, the residual spectrum, and we can look for molecules like water and CO that we expect in planets. This is the beta pictoris signal, and when you say, okay, and where do I see any molecular features in the image? And then you suddenly see the planet actually appears, the star vanishes, and you see the planet very clearly visible at a signal to noise of 35 or so. Now, here are some other examples, and the way we do that at higher spectral resolution to the right. This is of beta pictoris b, showing that it actually rotates, it spins very fast with about 25 kilometers per second. And on the right, we see a recent measurement by Sebastian Haffert, who uses MUSE to probe H alpha and two still forming planets in the PDS-70 signal.
I think you need to wrap up.
Okay,
we have only
this
1
is what
minute
you can
left.
do with the ELT. Two exciting measurements. We can do Proxima b very well, both in actual thermal emission and reflected light. And I want to have one important slide in the end, because this is really, it hooks on to you, Günther. There's a very important thing is going on at ESA. Now we're going to plan for the next half a century or so. And yeah, I think it's really important that Exoplanets is actually up there. This is really thinking beyond the ELT, beyond Earth-like planets around M dwarfs. This is really for true Earth analogs around Sun-like stars, for which we will really need an actual mission in space. I thank you very much.
Thank you very much. So,
thank you. Can you hear me?
Yes, we can hear you, Conny.
Okay, that's great. Thanks a lot. Thank you, Ignas, for this fascinating talk and very exciting outlooks for the very near future. So I'm going to try to transfer some questions. So the first one from Eliak, how about the hot Jupiter Kelt 9b? With a 4,000 temperature, the atmosphere would probably have a thermally driven wind. Can you comment on that? Is it possible to disentangle between proper motions of a hot planet around this host star and the atmosphere outflow?
Yeah, this is a very good point. So I glanced over this, but so what you saw is that the velocity of the iron changes during the axial transit, and there are several aspects to this. First of all, the exoplanet is spinning. So a part of the atmosphere you expect to go towards you, and the other part is going actually the other way. And then there is a global wind blowing from the day side to the night side. And then there is also that the planet is moving around the star. So that there are three different velocities you have to take care of. And then you have to take into account that actually apparently the atmosphere looks different on the morning side than it looks at from the actual evening side.
Okay, then there's another question from Stefano Vitale. Great talk. You did not mention Plato. This question is not from me, it's from Stefano.
I showed Plato. Yeah, Plato is going to be very important for the next phase, so to say. So I got a little bit stuck there in the end. If we really think about Earth, like the really true Earth-like planets around other suns, yeah, we need something like Plato to actually find them.
Okay, and then maybe in the interest of time, a final question from Alexander Shulevsky. Do you know whether anyone has looked in more detail at the stars reported recently by LOFAR to have associated radio transients? Any planets there?
Yes, I know people are looking at that. I think I'm not allowed to say anything, but it's really nice. I really like this.
Okay. Thank you. Let's continue some more discussion over Slack. If there is any interest still, please keep on sending questions, but let me thank Ignas now and move to the second speaker of the plenary. It's really a great honor for me to welcome the Director of Science of ESA. It is a good tradition that the director at each EAS meeting gives an overview of the highlights of the ESA scientific program. And I have to admit that Günther, among the several directors that I have been working with, gives by far the most fascinating talks among them. So without further ado, I'm going to give the floor to him and let's hear about really some interesting science results from ESA missions. Günther, please.
Thank you very much, Conny, and thank you also, Ignas, for the nice transition. Do you see my slides?
Yes, I do.
Yes, okay. And indeed, it is a tradition now. This is my third time that I give this presentation. Last year it was in live, Lyon, but the first time I also gave it remotely. So this is another tradition. And I'm very glad for so many audience, people in the audience. So let me start. This is an astronomy mission, an astronomy conference, but let me start with some exciting new developments in the solar system, because the sun is also part of astronomy. We have these charts of the fleet of the ESA missions. This is the one in the solar system. And you see that we have a lot of accumulation here in the inner solar system. And I just wanted to give two highlights, one from Solar Orbiter and one from Bepi-Colombo, that have recently done very interesting things. Let's start with Solar Orbiter, which was launched in February.
T-minus 10 seconds. 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. And liftoff of our solar orbiter and international collaboration to give us new images and a better understanding of our life-giving star.
Yeah, one of these launches is always a great excitement, and this was one of the most beautiful launches that we have ever experienced. It was launched from Cape Canaveral by our NASA colleagues, and originally it looked like the satellite would go to the moon, but it just made it right into its orbit to the sun. And this reminded us of the Bepi Colombo launch, which was only 1.5 years before from Kourou, which was similarly beautiful. And now we have two powerful missions in there. And actually Bepi Colombo has done something important. It is on its way to the inner solar system, wants to reach Mercury, and it has to do several flybys through several of the planets. And around Easter this year, it has done a flyby around the Earth. And that was really in the middle of the Corona crisis. And it was very reassuring to see Bepi Colombo looking down on the Earth, basically where we are sitting with our problems. And this is a nice movie that Bepi took itself. But we also had some of the scientific instruments switched on. And so in particular, the magnetic field measurements and the particle measurements were quite interesting. Here you hear the magnetic field, and now it becomes quiet when Bepi enters the solar magnetosphere, the Earth's magnetosphere. And this is very important for all kinds of near-Earth solar Earth terrestrial connections, the plasma physics. And it was very nice that we were able, despite the difficulties with Corona, to switch on our other solar system missions, Cluster, Solar Orbiter, and they were all measuring simultaneously. It's a kind of heliospheric orchestra that has now cross-calibrated itself and is ready to go. Now coming quickly to Solar Orbiter, that also has done something very exciting, but let me first show you here. This is a ground-based picture of Bepi Colombo flying by. Now it goes into the shadow of the Earth. This is the first time that the solar panels did not receive power from the sun, so we were a bit worried, but everything worked fine. And after 20 minutes or so, it reappeared. And this set of images is one of the ones that actually won a prize for the most beautiful ground-based images of Bepi Colombo. Now coming to Solar Orbiter. Solar Orbiter has, as I said, done something exciting. There was this comet Atlas that was discovered in 2019, and it actually split up into many different parts. So these are Hubble Space Telescope pictures from the comet 3 days after each other. We were thinking that by that time the comet is good, but then one or two of the bracelets have actually started to light up again. A few days later, that was almost a comet again. But in the meantime, it is a dude. It has vanished completely. But it was found out that Solar Orbiter is actually just by chance serendipitously flying through the tails of the comet Atlas. And that has happened by the end of May, early June. And all the instruments that were in situ measuring the particles and the magnetic field were on. And we cannot yet say whether we have seen the tail. The jury is still out, but this is a space to watch. It's very exciting. And this is just a preview of what we are planning for the future. We have selected a new mission, which is actually planning to fly directly through a comet, but this time through a comet that has never been seen before, that has never visited the solar system. So a fresh young object, or even an interstellar visitor. So now I would like to leave the solar system space, and I will move on to the real topic of the conference, to astrophysics. So this is the astrophysics fleet. And again, we have 5 missions in orbit currently operating. And there's a new kid on the block, Cheops. And that is linking very nicely back to Snell's talk because this is a dedicated exoplanet mission. Cheops was launched in December last year. And despite the difficulties, again, with Corona and everything, it's now working beautifully. It does very accurate transit light curves, and the point spread function is so good that we can actually get higher accuracy measurements than expected before. So this is something for the whole orchestra of exoplanet missions that is coming. This is the first one. And that brings me to the Hubble Space Telescope. Hubble has celebrated its 30th birthday in the recent months, and this was again, unfortunately, had to happen online and not live, but it was really moving to see how many activities happened on social media. People were baking Hubble cakes, and there were many meetings that were celebrating this birthday. In addition to this beautiful picture of the two nebulae in the Magellanic Clouds that was published on the celebration. And Hubble has also done some very exciting science in the meantime, as usual. And I just pick out one of them, which is very close to my heart, which is actually the first direct evidence for an intermediate mass black hole. This is an object that was originally discovered by Exoplanets Newton. It is a so-called tidal capture event, where a poor star is getting so close to a black hole that it is tidally disrupted and eaten, and is basically the last cry of help is radiated in X-rays and gamma rays. And this is what Exoplanets Newton and Chandra had observed in detail, but they could not localize the object very well. And then Hubble came and was actually able to identify this object to be in a globular cluster, but not a globular cluster of our own galaxy, but of another galaxy. So we actually have a distance, and we can now determine the mass of this object. And this is a nice animation of this several 10,000 solar mass black hole, which is in the middle of a globular cluster of another galaxy. And this is actually the first direct evidence of such an intermediate mass black hole. But in the meantime, ALMA has also measured several candidates for 10 to the 4, 10 to the 5 solar mass black holes close to our galactic center. So this seems to become a new type of object. And that brings me to the exciting microlensing events that Gaia is studying. Gaia is, I mean, you know, our working horse. It is publishing more than 1,000 papers. Last year, it has published 1,400 papers, and so 3 or 4 papers every day. And so it's very hard to pick out the real highlights, but I show you 1 or 2 Gaia highlights. This one is very close to my heart. This is actually connecting to microlensing. You know that when you are looking at a dense stellar field, like the bulge or the Magellanic Clouds or the Andromeda Nebula, then it can happen that one dark star is moving in front of a brighter star, and through the gravitational lensing effect, you are getting an amplification of the signal of that star. And many projects have looked for these microlensing, Machos, Eros, Orgel, M31 with the hypersubprime camera, and then also WFIRST has one element of microlensing. And indeed, when you look at the microlensing light curves, they are very I mean, they are colorless, so they look the same in the blue and the red. But some of these microlensing events take very long. So here is, for instance, one of the events that takes almost 2 years in total. And this type of microlensing events was not able to be discovered so far, only since these projects are now going on for quite some time. We have these longer microlensing events. And the longer the event, the more massive is the body that is doing the lensing. Now, interesting enough, Orgel has detected 60 of these long duration microlensing events. And for 20 of these, roughly 20, I think 19, Gaia has actually been able to determine parallaxes, and therefore we have distances to the background star, and therefore we also have rough distances to the lens. And these distances are surprisingly only a few kiloparsec. They were looking at the Magellanic Cloud or the bulge, and they are much closer to us than the distance to the with the distance, we can break the mass degeneracy, and we can actually estimate the masses of the lenses. And surprisingly, the masses of the lenses are between 1 and 10 solar masses for these 20 objects. If you would have a 10 or 5 solar mass object, a normal star at a distance of a kiloparsec, that would be a relatively bright optical object. And the fact that these objects are not seen in the catalogs means that they are very likely black holes. And these black holes are actually overlapping the mass gap, which is so far thought to exist in nature, where you have the neutron stars on one side and you have the stellar mass black hole on the other side. They are exactly in the middle. And this ties in very nicely to a very recent LIGO measurement. you know that LIGO and Virgo is measuring these mergers of black holes where you typically have, say, 10 to 30 solar mass black holes, which are then merging into 20, 30, 40, up to 80 solar masses. Then we have the electromagnetic black holes, which are thought to be the endpoints of stellar evolution. And we have the neutron stars, which themselves can merge to each other and then maybe can give black holes. But now LIGO is also finding first effects of mass gap events. So this is the recent event where there was something like 2.5, 2.6 solar mass black hole, which was merging with the 20 solar mass black hole, the first time a very anisotropic mass ratio. And this is exactly overlapping the Orgel Gaia events. So for me, the plot is thickening that there is something wrong with the black holes. And indeed, there is the speculation that black holes could actually provide the dark matter, which is getting more and more exciting. Okay, and this brings me to W First, which is now renamed to the Nancy Grace Roman Space Telescope, because W First actually has a mirror size which is big enough that you can not only measure a microlensing event in terms of the amplitude amplification, but you can also measure the little motion that the lensed star is making when the black hole is moving in front of the stellar field. And this is actually, in principle, one of the goals that the Nancy Grace Roman Telescope will have. And as you know, ESA has joined this project, and we are actually contributing in particular also to the downlink capacity, so we can bring more data down so that we can focus on these microlensing aspects. So very bright future for the black hole story in the future. Not only the exoplanets will be with us and will be very bright with the orchestra of exoplanets, but the black holes will probably follow the exoplanet route and become a very exciting topic. And this brings me to another one of these exciting Gaia results. Namely, in the meantime, we are actually looking with Gaia also at spectra of stars. And through the spectra, we can determine the local star formation rate. And this is from a Nature paper that has been published recently. And you see that the star formation rate close to the solar environment has actually changed over the last billion years. And there are these pronounced peaks in the star formation rate, which now have been associated with the likely trigger by the Sagittarius dwarf galaxy. And when you look at the orbit of the Sagittarius dwarf, it is coming, it is actually then crashing into the Milky Way. The first time that happened was likely 5.7 billion years ago. And this is very likely connected to the formation of our own solar system. So you see that our sun is basically exactly in this peak. Then it goes on, and after another 3 billion years, it comes back and it does another crash, and this is creating another set of stars. Then it flies back and comes again with another peak. And currently it is again in the Milky Way, and it is again producing additional stars. So if this is true, this is really fulfilling the promise that Gaia is unraveling the composition, the history of our Milky Way, our galactic home. But this particular result is very appealing because it connects us directly to the Milky Way and to Gaia. Okay, and with this, I would like to come to the future plan. Actually, Stefano Vitale already in his talk yesterday has promised that I will talk about the future of the program, as I always do. This is actually a new incarnation of our long-term plan. We had to fold in several new things. I mean, we had to fold in the results from the ministerial meeting in Seville, which was very successful, which enabled us to put Lisa and Athena on a clear financial footing. But we also have to fold in several other new developments. The COVID crisis will have an effect, and several other demands from the other missions will also have an effect. So we are currently discussing with our advisory structure and with our science program committee the new future. So this is only a draft plan so far, but it shows actually a nice history over 20, 30, 40 years. In brown, yellow, you see the large missions. And you see that in the future, we are currently in the JUICE project. In the future, we have TRUTH, Athena, and LISA. And each of these bars starts when we are formally adopting the mission. And then this is the launch, and then this is the operation phase. So you see that's one of these large missions is really carrying us through at least 20, sometimes 30 years, including the preparation and development. Then we have the medium-sized missions, the M-class missions. And currently we are in the luxury that we have launched Solar Orbiter. We will launch Euclid in 2022. We will launch James Webb, which for us is also a medium-class mission. And we are preparing Plato, Ariel, M5. So we have a very rich program with about 6 launches in 4 years, and then a large number of missions in preparation. So, there's also a very nice distribution in the program. We have interjected these smaller mission elements. Cheops, as I mentioned, is already launched. We are preparing a joint mission with China, SMILE, which is a solar Earth terrestrial connection mission. We have selected the first fast mission, Comet Interceptor, and we are discussing with our member states that we would like to include another F-class mission somewhere in the early 2030s for a launch. But the big blocks will be LISA and Athena. The bringing sound to the cosmic movies is still a very important topic, and it is also very important for us that LISA and Athena will be able to work together for about 10 years. Also, the detailed implementation timescale for LISA and Athena is still under discussion. Both of them are really huge projects and very complicated missions, and therefore we have to be very careful how we put them in. We are planning to adopt Athena next year, so that means that we go ahead and cut metal. But the adoption of LISA will have to wait for a few more years before the technological preparation is ready. But the future looks really very bright. And then in the previous talk, there was also the mention of Voyage 2050. This basically is the whole cosmic vision block that we are looking at. But now we are preparing and planning for the future, for the big missions after LISA and Athena. And you know that we have asked the community to submit white papers and proposals. We had a workshop a few months ago in Madrid where several hundred people were discussing, and we got a very large and exciting number of white papers, about 100 white papers, about 3 times more than in the previous exercises. We had about 200 applications for members of the topical teams, and we have selected 5 topical teams, and we got about 10,000 responses from the broader public community. And these teams are now, despite the COVID situation, they are working very hard, and we are actually hoping that we will get the recommendations later this year so that we can publish the next strategic plan for roughly the fall this year. And with this, I would actually like to stop. I have sped up my talk a little bit because of the technical problems, so I'm actually finished. I thank you very much for your presence and your excitement. Just to remember, I'm here in Madrid, you are here in Leiden, and all of you will probably be distributed over Europe and around the world. Thank you very much.
Thank you very much, Günther, for this fascinating talk and nice outlook for the future. Many things ahead of us. So I encourage attendees to post their questions. I will start with the one from Alexander Szelewski. How are ground segment support long-time operations folded into the missions? Is funding sufficient? Well, that's a tough. You plan long-term career paths for young scientists and researchers accordingly. So can you say a few words about that?
Yes, so we are in the kind of luxurious situation, but also a little bit problematic situation that all of our missions are currently running much, much longer than they were originally anticipated. When you think about SOHO, for instance, 25 years, Hubble, 30 years, Exomem Newton, 20 years. So it's really amazing the amount of science that we can get out of these missions. But this is also putting pressure on the operations fund, not only of ESA itself, but also in the member states, because all of these missions are done in cooperation between ESA and the member states. Gaia is such an example. Gaia is a huge machinery of several hundred people working in the community for the data analysis. And we always have to carefully balance the costs for the operations with the new missions. Currently, we are still okay with this, but I think it's also, we are right now in a phase where we are launching new missions like hot bread. Every few months or so we have a new mission, and the new missions, they basically have their operations for the first few years already funded, so that will actually release the pressure on the operations of the longer term missions a bit.
Thank you. I, for the moment, don't see any other questions. So maybe since I'm always caring more about the youngsters than the oldies, say a little bit more about Voyage 2050 plan in terms of topical themes. Is that possible for you?
Yes. So, I mean, you also had the question about the career path. You know that I showed that one of these missions, the large missions, typically is a whole generation mission, 30 years. And what you need in space science is patience first, perseverance. You have to keep on the job. And we in particular need a lot of the young people that are already getting excited now in order to prepare for the future. And so it is very nice to see that. So we have 5 topical teams. And the applications and the responses to those topical teams was quite reassuring that we had a rather large young generation there, and very nicely also in the young generation a better gender balance than in the typical classical scenario. So indeed we have 5 topical teams. They are not sorted according to exactly solar system, cosmology, etc., but they are more bridging over. There's also one on fundamental physics. And the idea is that this senior committee, which is 11 senior scientists together with about 50 topical team members, they will actually select the next 3 teams for the large missions. So that will be prescriptive because for the large missions, when you think about LISA or even Athena, you have to do a lot of technology preparation. We heard from Stefano Vitali yesterday that LISA Pathfinder was a technology preparation mission for LISA, which was done a few years ago. And so the whole history for such a large mission is more than 30 years. And therefore, we now need to identify what are the topics for the next 3 big missions in order to be ready with the technology when we want to fly them. Simultaneously, we are asking them to give us topics for medium class missions, but without being prescriptive. I mean, just to highlight future scientific excitements. I have participated personally in the Cosmic Vision exercise, and the big topics are not changing that dramatically, but there are really new effects coming, like what we have seen. The direct imaging of exoplanets is clearly something. Fundamental physics, where you might use atom interferometry in space to get much more accurate measurements and so on. So we are really excited that there are so many ideas from the community. Will not be easy to select.
Okay, maybe the question from our president. Thanks for a terrific talk, Roger says. International collaboration is playing a big part in all these plans. Where do you see the biggest challenges in forging collaborations with China and the US? And we have 1 more minute for you to answer that.
Yes. So with the US, actually, it was always a bit challenging that our planning cycle is 25 years, while they have their decadal surveys. But I think we have developed a very good scheme where we inform each other about our priorities. But I think in the future, we will always look at minor contributions of the agencies in our flagship mission. So we will, if possible, join the next NASA flagship mission. They will join our flagship missions. But I think we are not looking at the real 50-50 cooperations anymore, which are much more vulnerable and complicated. Mm-hmm. Contrary, in China, we are actually very happy that we have a bilateral cooperation on the 50-50 level, where we are really learning from each other. We tell China how to do the bottom-up process. We also learn from China how you can fast produce excellent technology and how you can push missions through in a very fast timescale. So each of these international collaboration partners has their virtues. And I don't want to forget Japan, which is really a strategic partner for us in many of our missions.
Okay, then maybe a final question connected to that from John Merle. He asks you if you see a role for ESA for small satellite missions like CubeSats, or is that more for national agencies and even institutes? How do you see this?
For ESA as a whole, yes. I mean, the science program is only a small part of the total of ESA, and ESA is actually launching very soon a rocket with a lot of, I think, 53 small satellites. We already have launched CubeSats together with CHEOPS, but they are not so much for the science program. They are for operational means, for technology, for communications. I think a CubeSat mission for science is probably something more of a national program.
Okay, and then a final question, if I may, from Naumeka Uwamwaza. The data for which these missions are they publicly available and used for free? I want to ask you this question because we also care about global.
Yes. Actually, we have a huge data archive in Spain here at ESAC. And more than 50% of all of our publications are coming from using the archive. All the data become publicly available after a nominal period of proprietary time. When you think about Gaia, for instance, our big flagship mission, all the data are public immediately. Also, it takes a long time to make them public because they have to be analyzed and so on. So we are getting more and more into this community science engagement, and more than 50% of our outcome is actually through to the archive.
Yeah, so with that, I think it's time to close the session. We have an outlook for the whole world to work with ESA data, as we just heard, and there's lots of things to do, many more data products and stars and planets than astronomers to analyze them.
Yes.
So yeah, it is that we're working towards as much as we can open data policy.
We need all your brains. Thank you.
To thank Ignas and Günther again for two fabulous talks, and for the community listening on, please have a great lunch and see you in the afternoon sessions. Bye. Thank you.
Excellent. Thank you. Bye.